To that end, I thought it would be worthwhile reflecting a little bit on what we did yesterday. I was giving a version of this boot camp in Sydney, Australia back in February. One of the things they really liked was a retrospective I just started doing sort of spontaneously at the beginning of each day on the contents of the previous day. And I was surprised at how much it was appreciated, but maybe I'll try the same here. So yesterday, we got our first taste of AnyLogic as a group. We took a look at a model up front, which involved the spread of infectious disease in a stylized space, with individuals connected to neighbors, spreading in a very localized sort of way, in regular way. But saw that even with a quite simple model structure and a quite simple, very straightforward sort of space and connectivity, you could get very interesting patterns in the we had patterns that came out of it, which were nowhere directly programmed into the model. They weren't presupposed by model design. Instead, they were reflected emergent behavior, which was where the behavior of the whole is greater than the behavior than the sum of the parts, where we couldn't point to any one feature which gave rise, say, to those concentric, to those circles or the waves of infection, but where instead a combination of different factors interacting over time gave rise to very interesting and textured spatial structures and temporal structures. One thing I sometimes do with that example is to graph out over time, for example, the number of infectives in that population. And as you might expect, it sort of rises from a low level, reaches some peak, and then declines some due to sort of limitations on the space, etc. And the fact is that while behavior over time graphs like this can lend a lot of insight at an aggregate level, there are some aspects of the situation, the spatial structure, for example, which are missed in this. And being able to visualize that, the spatial spread there, helps us clue in to additional sorts of what in system dynamics are sometimes called reference modes, in this case spatial reference modes, additional sorts of patterns that we may want to help validate or explain with our models, and help provide a generative explanation for where these patterns are coming from. So, for example, rabies, a disease associated with sometimes waves of infection that spread out in similar fashions. These agent-based models that we're working with, because they do so readily capture spatial structure, they capture temporal structure, the behavior over time, but also topological connectivity of individuals within networks. They're very powerful vehicles for what we sometimes call pattern-oriented modeling. This is a term coined by Grimm and so on. Again, one I didn't have time to go into in the class because of the limited schedule available. But often we use these models to try to explain, reproduce patterns we see within the world of a wide variety of sorts, not just these temporal ones, but spatial and topological as well. We continued on to discuss yesterday a variety of basic subcomponents within these sort of models. So we built up models, for example, within the AnyLogic interface that included some basic elements of heterogeneity. So we had individuals within the population represented by agents who differed in income and sex, for example. And we started to see how we needed to tag those particular properties, those particular data items, with an indication of what sort of data item they are. For example, color? Are they an integer? Are they a double, or are they a double precision value? Or are they a sort of Boolean value? We saw that we could quite readily introduce heterogeneity into the population through description of probability distributions from which the values were drawn associated with the surrounding population. So population being responsible for creating the agents, we look to the population to specify the probability distributions from which agent values are drawn. But those probability distributions we specified were simply formulas. They were expressions, as we say in Java, that computed some value. And we could have, for example, instead of imposing a probability distribution, we could have drawn the properties of successive individuals from a database, for example, or from a spreadsheet file, or what have you, and created a synthetic population that mirrored some real-world population. So AnyLogic's mechanisms as far as instantiating these agents, specifying their properties, are very flexible and afford themselves easily to specification via in a probabilistic way, but also by drawing them from diverse other data sources. We continued on then to look at one of the major mechanisms, not the only certainly, but a major mechanism for introducing agent behavior in the form of state charts. Here we have an agent's state with respect to one particular factor, say with respect to HIV infection, being defined by a set of states that are mutually exclusive and collectively exhaustive. For the particular simple case we looked at. Agents' characteristics and behavior over time can be specified with respect to several of these considerations at once. So for a given agent, you might have a state chart representing their progression in terms of diabetes, and another state chart in terms of their progression in terms of tuberculosis. The two are not total solitudes. The progression in your diabetes, in as much as it's affecting your immune system, for example, may impact TB. We could also have state charts associated with behavioral risk factors like smoking, for example. And once again, you get interactions there. Smoking impacts risk of TB, both because of impacts on cilia in the airways, and also because of impacts on lungs and immune function. It also interacts with diabetes. But the key point is we can kind of decompose an agent's state and an agent's behavior over time, their evolution over time, using state charts as a very convenient vehicle. We don't have to deal with all possible combinatorial explosion of all possible states they could be in with respect to all of those, as we would in a classic compartmental model. Instead, we could have state charts for each one, and we could insert very artfully connections between those state charts where desired. Otherwise, they can play out in a largely independent fashion. So state charts are a very powerful vehicle for describing basics of agent evolution, comorbidities, and a variety of other factors. We'll be seeing later how we can use other tools, also declarative in nature, where we specify the what is needed, and AnyLogic takes care of the how. We'll see other tools for specifying agent behavior, for example, in the form of stops and flows. Situations where you have an agent behavior changing continuously over time. Perhaps it's their a quantity such as their number of infected cells in their epithelium that are infected. Such a large quantity we treat as continuous. Or perhaps it's quantities such as income, or perhaps it's quantities such as self-regulatory capacity, which may be varying depending on both internal dynamics and external situation. So state charts are one mechanism for declaratively specifying agent behavior within AnyLogic, but they're not the only mechanism. We saw with state charts that we had a variety of transitions by which we could transition between states. Could people help suggest what were some of the transitions we saw yesterday? Some of the types of logic that by which someone might be triggered to go from one state to another state. Timeout was a good one. So that occurred after some fixed amount of time exactly. So they come into the originating state, and maybe the timeout is 10, and they'll leave exactly 10 time units later, assuming they haven't left by some other transition in the meantime, assuming they haven't disappeared altogether, they'll leave via that transition 10 time units later. It's worth bearing in mind that timeout, well, it does specify a specific time for any one case. That timeout might differ between individuals. It might differ even for that individual in different circumstances. For example, maybe we're representing an individual's behavior with respect to jobs. And they might have jobs which where they'll leave after exactly some amount of time, but that time we might draw, for a particular job, we might draw it from a distribution, and then they'll leave after exactly that amount of time later. So timeouts provide a way of actually imposing arbitrary distributions on how long someone stays in that state. You can draw that timeout from a distribution, and then it'll be preordained they're going to leave via that if they haven't through some other transition in the meantime. So timeouts was one. What are other ones? Sorry? A rate. So there we had some hazards of chance per unit time that they would leave, and it all came down to a matter of chance. It's a memoryless process. They have some chance per unit time, and sometimes they stay longer. Sometimes they sometimes leave more quickly, sometimes less quickly. Although I didn't talk about it, we certainly, I didn't discuss in detail, you can use the rate-based approach to have time varying hazards. So some of you may be familiar with survival analysis and deriving hazard rates associated with risks such as development of some condition over time, perhaps it's development of active TB following infection by the TB mycobacterium. Maybe it's development of end-stage renal disease following development of diabetes. And there we could draw a hazard over time that varies, and the chance rises over time, for example, based on how long you've had diabetes, that you'll develop end-stage renal disease within the next month. So we have a rising hazard. And we can capture those with these rates as well. We just have to be careful that it sort of recomputes. It knows that rate is changed and recomputes additional. What were some other, those are the two we concentrated on yesterday, but there were a couple others. Anyone remember? Okay, message one. Excellent. So when the agent receives a message, such as an infection message, but it could be a message that conveys information. It could be a message involving some social influence, for example. It could be a message involving influence from some promotion of a product or of some advertisement for fast food or something like that. They receive this message and they can be influenced by it. Now, if you have a message if you have a transition predicated on a message, say going from susceptible to infected, if a message comes in and someone's in a susceptible state, they can then take that transition. We didn't show it, but you can make it guarded by a certain chance they'll actually take it. So it's not preordained, they'll definitely take it. So it could further check other conditions, or it could roll a dice and see do they in fact take it. But if they're not in that state, they were already infected, or they were already recovered, and there's no transitions from those states that depend on the message falls on stony ground. In fact, it doesn't actually trigger any change in them. So remember that message handling is dependent on what state you're in. It's if there's a transition out of that state in which you're currently located right now, because that's triggered by a message, then it won't get processed as such. One thing we also didn't show yesterday was that any logic provides a very general mechanism for routing messages among state charts. So if a message comes in, that message may have to go to different state charts depending on what sort of message it is. For example, maybe some sorts of messages relate to your exercise habits. You know, there are social nudges as to your exercise habits from your social network. Maybe other messages have to do with infection or different conditions. Maybe it's HIV, maybe it's Hep C. And you'd want those messages to go to different state charts to route them to. And in any logic, if you look at my online lectures, I talk about where the place where you can do that. It's in the agent properties. You can indicate which state charts you want messages to, or you can put an expression that says, this message to this is this state chart, that message to that state chart. It's kind of wired up by default in any logic for the simple case, but you can change that. So message was another extremely important one because it had to do with agent interaction. It's probably it is the most common way for agents to interact in law. Not the only one, but the most common one. There are some others too, we'll see today. Arrival of agents, for example, at a destination. Situations where a condition is in place, so the agent will transition when that condition is met. Those are examples of additional types of logics you with transitions. Okay, so we saw a basic understanding of sending and receiving messages between agents. Agents could send messages out, whose target could be specified either as a particular agent, such as themselves, or such as a known agent like their mother or what have you, or it could be sent. Messages could be sent to a class of agents, specified in a declarative way that any logic figures out exactly who that is and takes care of picking one of them and sending it to them. So, for example, what were two classes of agents we saw messages being sent to in the course of yesterday? Okay, you could send it to agents in general, any random agent in space. That was actually one we saw sort of in passing in my comments. But what are two other classes? Okay, so with the infection message, we saw that there were actually two different cases. One where the message was sent to all my neighbors in space. Another where it was sent to my neighbors in a network, random underbar connected the neighbors in the network. I think it's random underbar neighbors for neighbors in space. Okay, so any logic allows you to just sort of specify this, and assuming that you're in a space, will take care of sort of figure out who your neighbors are. Are they north, south, east, and west, or are they those at different directions? Who's actually there, et cetera, and send messages to them. Okay, anyway, those were some basic things we saw yesterday. Late in the day, we had some further discussion about references and classes and objects in any language. So we have these in Java. So we have a class, which is kind of like a mold. It specifies how do you make objects, and it dictates personhood or personness. What does it mean to be a person? And then you can create many specific persons, so-called instances of this class, or objects of that class. And those particular persons will then circulate with properties. They don't have to all be the same. There can be heterogeneity between them, but their behavior and what information is maintained, what types of information is maintained for them, are specified by personhood, by the characteristics of that class. And we saw we could have references to a particular person, and with a reference, we could get information from that person. We could ask, for example, about their income. We could double their income. We could inquire as to their sex and colors and differently accordingly. We could further, however, ask them to do something for us. So, for example, we could say, hey, agent, please give me your number of connections in your network. Or we could say, I'd like you to commit to this other agent. So we can make requests. We could ask them to compute some data for us, or we could tell them to change in some way, like by connecting to another agent or disconnecting or what have you. So once we have a reference, we can use that to request something, and sometimes what we get back is a reference to a different agent. So we say, give me your first connected neighbor, your first neighbor to whom you're connected. And they'll return a reference to this other agent to whom they're connected. And we can say, for that agent, give me your X value, your Y value. Okay? So we saw that late in the day. Any questions about that material before we start for today on new material? So that was my little retrospective. Yes? Sure. Okay, we're going to see that this morning. Okay. So we're going to see it for two cases. We're going to see it for a spatial case, for spatial cases, and we're going to see it for network cases. Okay. Great question, and it's one of those dependencies which will be addressed today. Okay. Other question? Yes. Yeah. So the answer is you can. We'll see today how we can compute some basic statistics on those who are in some class. Maybe it's of all males, what's the average income and that sort of thing. All males in this age category, what's the income. And we will see how to do that today. There's, in many models, a desire to keep track of that information on an ongoing basis. In other words, to kind of track statistics for different subdivisions of the population over time. And any logic provides basic mechanisms for doing this, but they tend not to be, efficiency is not their strong suit, and it turns out that there's more sophisticated mechanisms that you can put in place yourself, which will be rather more efficient. This is an area where any logic is investing quite a bit, and we're anticipating sometime in the next year or so, year and a half, probably a significant advance to any logic where it would automatically keep track of different subdivisions of population. I was just talking with someone at any logic about this issue, and it looks to be something which is coming quick. You can do a lot of basic things right now, and it's straightforward, and any logic eases it greatly out of what will be required in another type of package for agent-based modeling, and we'll see how the basics can be done today. Okay, great question. Other questions? Questions and material from yesterday? Things you'd like to see addressed? Okay, ladies and gentlemen, let us start our engines. So we're going to go into today a set of new topics, and are going to be addressing expanding our vocabulary for any logic. Now I've chosen to do these in an order that will let me merge together and mesh practical examples on several things. So my own didactic style is when I learn material, I often like to learn the concepts first and then applications, but many people like to see the application first. They like to see a concrete example and then go sort of explain it. And I'll be engaging in that sort of dialogue today. Okay, we're going to see some concretes. So there's some things I'm going to ask you to try, and then I'll come back and explain what in fact is going on there once you have that concrete understanding. So this morning we're going to be weaving together discussions of a couple of things. One is dynamic populations, dynamic networks to some degree, and events. Okay. One of the challenges associated with agent-based modeling is that it has quite a large vocabulary compared to other forms of modeling with which you may be familiar. For example, if you look at system dynamics modeling, you have a quite small modeling vocabulary: stocks, flows, auxiliary variables, and you can have sort of some additional things that you may want to distinguish, like constants or what have you, but table functions. But really, you're dealing with a very, very small vocabulary. Compartmentally modeling being the same sort of mathematical structure, it's the same thing. And you can do a lot with that. You can do a tremendous amount by sort of putting together those pieces in creative ways. Agent-based modeling, by contrast, has a large modeling vocabulary. We saw some of that yesterday. You have state charts, you have messages, and you have events, and you have spatial types and networks and connections, and you have all sorts of different pieces that in a given model you'll typically draw a subset of those to put together the types of, to capture the sorts of behavior that you're interested in. And a lot of today, some of tomorrow, will be spent continuing to build up your understanding of vocabulary, of how we do these things in any logic. How we put together these models in any logic, the pieces out of which we put together. So this morning we're going to be weaving together several subcomponents.